Let's now discuss the influence of the vertical tail on roll stability. So let's draw an aircraft here with a vertical tail, and here's our x-axis or our roll axis. So the aerodynamic center of the vertical tail, is somewhere usually maybe close to the quarter cord, back a little bit if you have some sweep. And then it will depend on whether that vertical tail is above or below, obviously, the x-axis or the roll axis of that aircraft, right? So right here, we're going to define this as h sub v. That's the height of the vertical. That's the height from the roll axis up to the location of that aerodynamic center, where we're supposing that the lift basically acts through that point from that surface. So we can write the influence on the rolling moment coefficient due to the vertical tail. And I'm just gonna put this in non-dimensional form. You should be able to see basically what where each of these components come from now that we've worked through this several times on other lifting surfaces. But we'd have SV, HV over SW, BW times the lift slope of the vertical with respect to alpha, multiplied by 1 minus epsilon s comma beta times beta minus epsilon s naught minus epsilon r delta r. Okay, so this is just an equation for the rolling moment due to the lift on that tail. And we can talk about the components of this really quickly. So this is the ratio of the dynamic pressures from the main wing to the vertical tail. Then we've got the area and the height divided by SWBW. That's because we've non-dimensionalized the rolling moment on the entire aircraft by using the area of the main wing and the span of the main wing. And so this coefficient here, though, was non-dimensionalized. This is the lift coefficient on the vertical. That's non-dimensionalized by the area of the wing. And so that's why we have this ratio here, SV over SW. And then we have to multiply that force by this distance, HV. And so anyway, that's why that guy shows up there. Okay, so then we've got the lift slope on the vertical. Beta is our side slip angle. Epsilon s naught would be our side slip angle with 0 beta, which you could have if this is behind a propeller or something. Epsilon s comma beta is our change in side slip or our side wash with respect to beta. I'm sorry, I think I called this side slip. This is the side wash. So this is a change with respect to beta. And then we've got epsilon r, so that's some efficiency of a rudder deflection multiplied by the rudder deflection itself. And usually this efficiency would be between 0 and 1, where 1 would be if the entire vertical surface rotates as the rudder, and 0 is if you have 0 rudder. So that depends on your flap chord fraction and how big that rudder is compared to the surface of the vertical. So anyway, that's where those components come from. And we can then take the derivative of this with respect to beta. So our roll stability derivative from the vertical is actually just going to be all of this stuff right here. So if we take the derivative with respect to beta, we get all of that stuff. And then if we take the derivative with respect to delta r, our change in rolling moment with respect to rudder deflection due to the vertical, it would be all of this comes in here multiplied by this guy here. Okay, so you take those two, the stuff out front, multiplied that by the epsilon r. Actually, it's just the epsilon r, not the delta r, I guess, technically. So let me just fix that there. Because we've taken the derivative with respect to delta r. Anyway, so this is our roll stability derivative due to the vertical. This is our roll control derivative, or our influence on roll due to a rudder deflection. Okay, so one thing, so if we just focus on the roll stability derivative here for just a moment, we notice we've got a negative out front, and then all of these terms in here are going to be positive. This is just a ratio. That's going to be positive. The areas are positive. This length is positive. Our lift slope is positive. 1 minus epsilon s comma beta is going to be most likely positive. And so what we find is that if HV is positive, that means that the aerodynamic center sits above the axis here. We will get CL beta less than 0. Okay, so if HV is greater than 0, CL comma beta due to the vertical is less than 0. So that means that it's stabilizing if the vertical tail is above the roll axis. Okay, it also means that it's destabilizing if we had a vertical surface below the roll axis. Then that would be destabilizing because the sign of HV would change. Okay. So this is just an approximation for the effect of the vertical on roll stability. We actually, in a previous lecture, learned that it's a little bit more complicated than this because if you look at, for example, a conventional vertical tail with a horizontal stabilizer, and then let's look at the lift on the vertical stabilizer. It's going to look something like that. And then and that's lift in the with some positive side slip angle. So we're looking from the back of the aircraft towards the nose of the aircraft. So we've got side slip coming in from the right hand side here. So it's going to create a lift distribution that looks something like that. And then on the horizontal, due to that, even if we have no angle of attack, just due to the pressure, the low pressure on the vertical, we're going to get a low pressure region that creates a lift distribution that will look something like this on the horizontal. Okay, so we'll have some lift on the left-hand side and some negative lift on the right-hand side. So what happens is that if we're looking at the influence of this, let's just pretend like the roll axis is right here in the center, then the vertical stabilizer is creating a rolling moment with positive beta that's in this direction, right? But the horizontal stabilizer is creating a rolling moment in the opposite direction. And so what happens is if we have this kind of a tail configuration, we usually want to decrease the value that comes out of here. So we want to decrease by maybe 25 to 35%. Simply due to the interaction of the horizontal. Now that's a real rough approximation, and this is for a conventional tail, okay, that you want to decrease it. Now that's, like I said, it's a rough approximation. Really what you want to do is put this into maybe a numerical lifting line or some simple code that, it's an inviscid phenomenon that can be fairly simply and quickly predicted by numerical lifting line or some panel method or something. So you can actually get what your real roll stability derivative is going to be due to this entire empennage, okay? And again, we have some approximation for what the vertical is doing, but it's a bit more complicated because it can interact here with the horizontal tail. Now let's look at one other case. Let's say that we went to a T-tail configuration. So in this case, this is the roll axis, and we put our horizontal tail above the vertical tail. And you see this, this is actually fairly common on aircraft. So now let's look at what happens here. So the lift on the vertical is going to look something like this with positive beta. Again, we're looking from the back of the aircraft towards the front. So with positive beta, we're going to get some lift like that that's creating a negative rolling moment. So that's stabilizing. And now let's look at the influence of the horizontal, which is going to have some lift distribution that looks like this now. Because of the low pressure over here on the left-hand side, we're going to get some downward force. And then the high pressure on the other side, we're going to get some upward force, okay? So that is actually, once we sum those forces about the roll axis, that actually is also creating a negative rolling moment. So it turns out that this interaction is actually stabilizing, and so we actually want to increase and again, just a rough estimate for that is increase by 25 to 35% for a T-tail, okay? So if you have your horizontal attached above the vertical, then that is actually it will actually increase your roll stability further, even more than what this equation is predicting here. Okay, so those are some of the interactions, and again, the best way to do this is to put it into some tool or some code to estimate your the influence of the vertical tail or the entire empennage on your roll stability, because there's some complex interactions going on back there. But as a first approximation of that, you can use this equation here and then offset that by 25 to 35%. Decrease it if you've got a conventional tail like this, or increase it if you're using a T-tail.